In a previous video, we presented the Stevens law, assuming that the pressure over the water level was zero.
But is it really true? Well, let's put a gauge here and see what will happen. Of course, it will indicate that the pressure is zero. Now, let's put it here, h meters below. It will indicate that there is a pressure. And we know how to calculate it. It will be gamma h. Well, we're talking about gauge pressure. Let's see how this device works. Here is one of them, as seen from the outside and from the inside.
There's a curved pipe known as a Bourdon tube.
This gauge is probably the most common type used in industry. It's a Bourdon gauge. It works like a potty blower. It rests when there is no pressure applied on it. When there is a pressure, the tube will extend, as it happens in the potty blower. Let's make a small change in the gauge. Let's close and seal this extremity. Let's do it at the sea level. Now we turn it like this
And close it. Inside the sealed pipe, there is atmospheric pressure, which is equal to the pressure in the outside. So the pointer is indicated 1 atmosphere.
We've just built an aneroid barometer. See how it works. It will indicate 1 atmosphere at sea level, but if we climb the mountain, the outside pressure will be lower, so the pipe will tend to extend,
And the pointer will show that the atmospheric pressure has decreased. The Torricello experiment allows us to measure the atmospheric pressure. We'll need the tube closed in one extremity, a small flat vessel, and some liquid mercury. We fill the tube with mercury all the way to the top. Then we put some mercury in the vessel. There they are, tube and vessel containing mercury.
Then we close the open extremity of the tube, turn the tube inside the vessel, but don't let the mercury leak out from the tube. And even so, the mercury level will go down inside the tube. Leave behind it what? Nothing but the vacuum. Hey, professor, that's not true. There will be mercury vapor.
Okay, you're right, but its pressure will be so small that we'll assume that it's just vacuum, which means that the absolute pressure here will be zero. But we'll talk about this in another video.
When this experiment is performed at the sea level in a sunny day, the mercury column will be equal to 760 millimeters.
So this is what we have. Point A, in which the absolute pressure is equal to atmospheric pressure.
Point B, in which the absolute pressure is equal to 0, and the height between them equals to 760 millimeters. The specific weight of the mercury is equal to 136,000 newtons per cubic meter. So,
writing the Stevens law for this case, we find the value of the corresponding atmospheric pressure, 103,360 pascals, or 0.1033 megapascals, as you wish.
Just for your information, UPAC, which is the short for International Union of Pure and Applied Chemistry, has established the standard atmosphere
equals to 101,325 pascals. But for our purposes, we say that at the sea level, the absolute atmospheric pressure is equal to 0.1 megapascal,
which is equivalent to 10 meters of water column.
Here it is, the aneroid barometer registering 0.1 megapascals of atmospheric pressure at the sea level, or 1 bar, which is another denomination for the pressure used in practice. If you go to the top of the mountain, the barometer will register a smaller atmospheric pressure. If we apply the Stevens law, we'll find this new pressure.
Whoa, professor! This is not right. Are you assuming that the air is incompressible? Yes, I am. It's okay for small elevations, say up to about 3,000 meters, and for regular engineering purposes. There are, of course, cases of precision in which we cannot assume this, but in general we can. The specific weight of the air
will be assumed equal to 12 newtons per cubic meter.
So we can write this expression by which we obtain the pressure in pascals, or this by which we obtain the pressure in megapascals, or this by which we obtain the pressure head in meters of water column. But as we've said, we can use these expressions for elevations up to 3,000 meters. Let's consider this pump. The height for its suction is limited, because the absolute pressure here at the top can't be smaller than 0. Whoa, Professor, this is not right. You are missing something. The pressure can't be smaller than the vapor pressure of the liquid you are pumping. You're right again, but we'll talk about this in another video. If the pump is installed at the sea level,
and we apply Stevens' law for this situation,
we find the highest value for H.
the absolute atmospheric pressure is equal to 100,000 pascals.
And the water-specific weight is 10,000 newtons per cubic meter. So H will be equal to 10 meters. Here it is, but as we saw, it's a theoretical value. In practice, this value will be lower because of the water vapor pressure, head losses. We will see this in other videos. But now, let's consolidate some important concepts. In engineering, we seldom talk about absolute pressure, only in very specific cases. So, in general, we say that when we are at the sea level, the pressure is 0. We use the gauge pressure. At the inlet of the pump, the absolute pressure would be 0, but we don't say that.
We say that the pressure is minus 0.1 megapascal.
Here's the Bourdon type manometer gauge that we've seen,
which measures the gauge pressure.
And here's the aneroid barometer that we've seen too,
which measures the absolute atmospheric pressure.
See what happens. In an environment where no gases exist, the absolute pressure will be 0. Let's have some atmosphere now. The absolute pressure will be equal to the corresponding pressure. At this point, we start to track the gauge pressure.
It means that when the gauge pressure is equal to the absolute atmospheric pressure, its value is 0.
And consequently, at the total vacuum,
is equal to minus absolute atmospheric pressure.
When the gauge pressure is P,
the absolute pressure will be equal to P plus absolute atmospheric pressure.
Absolute pressure is always greater than 0, or at the minimum equal to 0.
Gauge pressure will be greater than 0 if it's greater than the absolute atmospheric pressure, or smaller than 0 if it's smaller than the absolute atmospheric pressure.
Well, I think we have seen the most important facts about absolute and gauge pressure. Are you ready for more? We will see it in other videos.
Oh, and if you liked this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.